It is essential you are comfortable with atomic orbitals and the structure of an atom. Inside an atom there is a very small, dense region of positive charge, made up of protons and neutrons, called the nucleus. The nucleus is surrounded by negatively charged electrons that exist in atomic orbitals within specific energy levels or shells, labelled as principal quantum numbers, starting with the number 1 for the energy level closest to the nucleus. Atomic orbitals are regions of space where, if occupied, there is a 90% probability of finding an electron. Each atomic orbital can hold a maximum of 2 electrons, one pair. Electrons are negatively charged and repel each other, meaning only a limited number of orbitals can fit around a nucleus in a given energy level. As distance from the nucleus increases, however, there is more space available, meaning more orbitals can fit and be arranged around the nucleus in higher energy levels. Orbitals in a given energy level can have different shapes, meaning they can also have slightly different energies and belong to what are called subshells. S subshells are found in every energy level in an atom, and they contain only one spherical shaped orbital that is called an s orbital. As a result, an s subshell can hold a maximum of 2 electrons. P subshells contain 3 dumbbell-shaped orbitals that are too big to fit in the first shell, meaning all energy levels apart from the first have a p subshell. The 3 orbitals in a p subshell are called p orbitals and are labelled as px, py and pz. They all have the exact same shape and energy, only their orientations in space are different. A p subshell can hold a maximum of 6 electrons, 2 per p orbital. D subshells contain 5 orbitals that have different shapes, called d orbitals. The 5 d orbitals are too big to fit into the first and second energy levels, meaning only the third energy level and above in an atom can contain a d subshell. A d subshell can hold a maximum of 10 electrons, 2 per d orbital. As different energy levels can fit different subshells in, each can hold a different maximum number of electrons. The first energy level in an atom can only fit an s subshell and as a result hold 2 electrons. The second energy level can fit another s subshell and a p subshell, meaning it can hold 8 electrons. And the third energy level can fit another s subshell, another p subshell, and a d subshell, giving a total of 18 electrons. Electron configurations tell us how many electrons are in each energy level and subshell within an atom. They are written in a standard repeating format with a number, letter, and small superscript number. The first number represents the energy level, sometimes also called the principal quantum number. The letter represents the subshell, and the superscript number the total number of electrons within that subshell. They are always written in the order the subshells are filled within an atom. For example, if we go to the energy level diagram for the orbitals in sodium, there are 2 electrons in the n equals 1 energy level in an s subshell, 8 in the n equals 2 energy level with 2 in an s subshell and 6 in a p subshell, and 1 electron in the n equals 3 energy level in an s subshell. The electron configuration for this would be 1s2, 2s2, 2p6, 3s1. The 1s2 tells us that there are 2 electrons in an s subshell within the n equals 1 energy level. The 1 means the first energy level, n equals 1. The s means an s subshell, and the 2 means there are 2 electrons in this subshell. In the same way, the 2s2 tells us that there are 2 electrons in an s subshell within the n equals 2 energy level. The 2 means the second energy level, n equals 2. The s means an s subshell, and the 2 means there are 2 electrons in this subshell. The 2p6 tells us that there are 6 electrons in a p subshell within the n equals 2 energy level. 2 for n equals 2 energy level, P for p subshell, and 6 for 6 electrons. The 3s1 tells us, you may have guessed it, that there is 1 electron in a s subshell in the n equals 3 energy level. 3 for n equals 3, s for s subshell, and 1 for 1 electron. We don't actually need to draw out energy level diagrams to figure out the electron configuration of an element. We only really need to know the total number of electrons in the atom.